Let me introduce JOOMED, GLK's new multimodal LLM platform. Many of you already use general-purpose LLM platforms for work, study, and information retrieval. However, due to the inherent complexity of medical imaging, you may not have encountered a multimodal LLM platform that professionally handles both medical images and text. General-purpose LLMs may appear to provide answers about medical imaging. However, they have limitations when it comes to interpreting 3D imaging structures, performing quantitative analysis, detecting subtle lesions, and securely integrating multimodal data to support reliable diagnostic decision-making. To address these specialized medical imaging challenges, a dedicated foundation model is required, one that integrates a specialized vision encoder, domain-specific RAG built on medical expertise, and evidence-based reasoning. JLK now presents JOOMED, the platform built to solve these problems. JOOMED, as presented, is software developed for research use only, intended as a tool for clinical research by healthcare professionals. Interpretation of results is performed by the user, not JOOMED. Product features, launch timelines, and regulatory clearance status may vary by region and are subject to change. These terms are also specified in the JOOMED end-user license agreement. The JOOMED presentation currently provided in English is a version intended for potential customers outside of Korea. Please note that some terminology may differ. Today's presentation covers 5 main agenda items. Let me explain each in detail. First, let me discuss the limitations of general-purpose LLMs in handling medical imaging data like CT and MRI. Medical imaging has a fundamentally different structure from ordinary images. In particular, MRI and CT are not single images. They are 3D volumetric structures composed of tens to hundreds of stacked slices. Understanding the structural continuity, the context between slices, is essential to avoid missing even small lesions. It is high-dimensional biomedical data combining anatomy, physiology, and multiple signal types. Furthermore, medical images are not composed of RGB-like standard images. Multiple sequences such as T1, T2, FLAIR, ADC, and non-contrast CT each carry distinct information. Physicians review these sequences together to determine the true clinical significance of a lesion. One of the most challenging aspects is that many diseases manifest as microlesions measuring just 1 to 3 millimeters. Conventional vision encoders often treat these tiny lesions as noise or fail to detect them altogether, a critical limitation in clinical practice. Interpreting medical images goes far beyond simply identifying that something is visible. It requires understanding high-level semantic information, where the lesion is located in the brain, which functional areas it may affect, and how it appears across different sequences. In other words, conveying the complex clinical context that medical professionals expect demands an exceptionally high level of technical capability. Can you see the small lesion on the screen? This is a microbrain aneurysm measuring just 1.62 millimeters in diameter, often called a ticking time bomb in the brain. Lesions of this scale can be missed even by experienced specialists, and early detection can significantly impact patient outcomes. So, how do general-purpose LLMs handle such critical findings? As shown in the figure above, the key challenges when applying general-purpose LLMs to medical imaging analysis include difficulty recognizing microlesions, limitations in 3D spatial coordinate extraction, and insufficient spatial perception capabilities. Now, let me discuss the limitations of medical imaging vision encoders. Conventional vision encoders are models optimized for analyzing pixel or voxel patterns to segment or classify lesions. However, they face limitations such as structural and scalability limitations, missing clinical semantics, and challenges in integrating LLMs. This section is critically important as it directly impacts both cost and accuracy. 3D CT and MRI scans consist of hundreds of slices, with each slice generating approximately 1,000 to 3,000 tokens. A single patient's imaging data alone can require hundreds of thousands to millions of tokens, making direct input into general-purpose LLMs practically impossible. This inevitably leads to cost explosion and information dilution, and most critically, can compromise clinical reliability. The danger of applying LLMs to healthcare is not simply that they can be wrong. It's that they can be wrong while sounding confident and highly plausible. This is known as hallucination. In healthcare, the issue of hallucination is a serious concern. In Chapter 1, we examine the limitations of general-purpose LLMs in medical imaging. In this chapter, let me explain how JOOMED solved these challenges. For LLMs to perform accurate reasoning, automatic classification, organization, and standardization of DICOM input images must come first. Previously, medical image filtering relied on DICOM tags that varied by hospital and equipment, leading to numerous errors. Ensuring accuracy often required clinicians to manually verify each case, a time-consuming process. JOOMED overcomes the limitations of traditional DICOM tag-based filtering. Our AI accurately identifies various sequences, such as T1, T2, FLAIR, and DWI, then standardizes and anonymizes DICOM data to enable more accurate, image-based integrated analysis by the LLM. For stroke analysis in particular, the AI automatically extracts only the relevant sequences from numerous mixed modalities. DWI for ischemic stroke and non-contrast CT for hemorrhage analysis. Through this approach, JOOMED significantly reduces token costs and substantially improves analysis speed. As shown on the left, a single brain CT scan is a 3D volume comprising over 500 slices. Inputting this directly into an LLM can generate more than 300,000 tokens, a scale that is practically unmanageable in terms of API costs, processing speed, and context window limitations. This is why directly inputting full volumes into LLMs using conventional approaches is virtually impossible. JOOMED solves this problem through JLK's multi-technology engine, built on over 10 years of accumulated expertise. The result is a structure that dramatically reduces token usage while ensuring cost efficiency, processing speed, and analytical accuracy. Traditional medical AI has been limited to processing imaging, EMR, and radiology reports separately. However, in real clinical practice, accurate decision-making requires interpreting all of this information together. JOOMED implements a multimodal medical AI architecture that enables a single LLM to simultaneously understand and reason across PACS images, EMR data, and radiology report text. As illustrated above, hospital data is currently stored separately across EMR, PACS, and reporting systems. This fragmentation can lead to time loss, errors, and information gaps for clinicians. With JOOMED, this entire process becomes automated. The AI classifies imaging sequences, standardizes DICOM headers, and automatically matches EMR lab values and medical history, organizing everything into a format ready for immediate LLM analysis. The LLM then synthesizes this multimodal data to deliver evidence-based reasoning. Analysis results are integrated bidirectionally with EMR and PACS systems in real time, allowing clinicians to view LLM insights directly within their existing viewers. This enables healthcare professionals to focus on patient care rather than data retrieval. JOOMED is more than just an LLM. Hospitals can now automatically integrate imaging, EMR, and text data, and finally leverage LLM-powered reasoning in real time, establishing a new clinical infrastructure for the AI era. Stroke is a well-known emergency where timely response is critical. Yet clinicians cannot always be at their monitors. They may be on rounds, attending a conference, or resting at home after a shift. To support rapid response in any situation, JOOMED provides both web and mobile platforms. We have applied JOOMED to patient data from over 20,000 cases. Now, let me show you the results through actual clinical use cases. Next is the JOOMED system architecture. The JOOMED foundation model was developed through a proprietary process based on medical imaging and clinical knowledge accumulated internally by JLK, and consists of multiple agents serving various functions. It is available for both on-premise and cloud deployment. Customized integration with general-purpose LLMs is also available based on client needs. What you see here is the actual user interface of JOOMED, the culmination of all the innovative technologies we've discussed. As highlighted in the previous slide, the inherent complexities of medical imaging have historically made extracting meaningful features a significant challenge. Furthermore, The two main pillars of hospital systems imaging data, PACS, and text-based clinical records, EMR, have remained strictly siloed, creating clear limitations in organically integrating them. But JOOMED is different. It seamlessly integrates with your existing hospital infrastructure, encompassing both PACS and EMR. As you can see from the 5 key functional areas highlighted on the screen, JOOMED achieves true fusion of all patient data, from medical images to diverse clinical records, powered by our multimodal LLM. Because of this, JOOMED delivers intuitive insight beyond mere numbers, helping physicians comprehensively understand a patient's condition at a glance and support clinical decision-making. Delivered through a highly convenient and intuitive UI designed to respect the physician's workflow, it is a truly unified platform where medical imaging and clinical data finally become one. JOOMED provides evidence-based information to support clinicians' decision-making with quantitative data. First, it incorporates the latest treatment protocols and recommendation grades from global guidelines such as ASA and AHA, ensuring the reliability of treatment recommendations. For situations not covered by established guidelines, JOOMED prioritizes high-impact research from leading academic journals. Additionally, JOOMED can be configured to reflect treatment recommendations optimized for each country's clinical environment, including guidelines from the Korean Stroke Society and the Japan Stroke Society. In this slide, I would like to introduce one of JOOMED's most powerful and highly differentiated feature, the Similar Patient Search and Analysis. The Similar Patient Search and Analysis feature is not a simple keyword search. It is a sophisticated technology that computes multidimensional similarity based on deep, practical clinical understanding. Now, physicians can converse naturally with the LLM, asking questions like, "Show me a list of similar patients from our hospital's 10-year data," or "What was the 3-month prognosis for these similar patients?" With a simple question, vast amounts of historical data are instantly summarized. This feature can be utilized in various ways: prognosis reference, treatment strategy support, early risk factor identification, and systematic preservation and transfer of institutional clinical knowledge. This innovation transforms the overall hospital workflow. Ultimately, JOOMED's Similar Patient Search function serves as a valuable reference tool for developing care plans for patients, leveraging the hospital's accumulated collective knowledge. Next, let me introduce a critical feature in stroke response, the JOOMED Prognosis Clinical Research Model. Gaining an early estimate of how a patient's condition might evolve is crucial in stroke management, where time is of the essence, providing important support for medical teams researching response strategies. JOOMED analyzes multiple dimensions, including the patient's 3-month prognosis, discharge prognosis prediction, the probability of early neurological deterioration, YENDI, and predicted treatment effect to provide data for clinical research applications. Immediately upon a patient's arrival at the ER, even before any imaging is completed, the system generates prognostic reference indicators using only clinical data. This enables retrospective analysis to study hospital-specific initial response protocols. Subsequently, as imaging data such as non-contrast CT, CTA, DWI, and CTP are sequentially added according to each hospital's protocol, the system incorporates them to enhance prediction precision, enabling comparative research with clinical outcomes. This feature can be utilized across various research areas: clinical research on rapid response protocols within the golden time, drug development research for YENDI high-risk groups, algorithm development research for progressive precision enhancement, tracking studies on individual treatment effects by medication and intervention, and efficiency research on resource allocation such as ICU and rehabilitation. JOOMED's Prognosis Clinical Research Model serves as a powerful reference tool for data-driven strategy development research in an emergency medical environment, typically dominated by uncertainty. As a medical imaging-based multimodal LLM platform, JOOMED enables in-depth review of medical images, AI analysis results, and various clinical data, including statistical visualizations. It also provides specialized features for labeling medical imaging data and building structured datasets for training. In short, JOOMED is a medical imaging, specialized LLM platform that supports precise analysis of diverse medical images and granular data management. Now, let's watch a demonstration of the full range of use cases. What you see here is the main screen of JOOMED. Patient data can be uploaded manually or automatically imported by integrating with the hospital's PACS or EMR systems. As soon as data is imported, anonymization is automatically applied to protect patient privacy. Additionally, data is systematically classified by patient, study, and series. Through the thumbnail view, you can view medical images conveniently and intuitively at a glance. As you can see, individual thumbnails can also be controlled in detail. Clicking on Statistics displays various statistical graphs related to imaging data and AI analysis. These are features developed based on JLK's extensive experience in medical big data management and analysis. When you click on a patient ID, you can see the timeline of images taken for each study at a glance. You can also see various linked clinical data sorted by their respective criteria. When you select a study of interest, you are taken to the detailed information screen. Here, you can see not only the original images, but also the quantitative analysis results from real-time AI algorithms, ICH-CTL. Now, let me click the AI button on the right. You can then view more detailed analysis results from various JLK AI algorithms, MSV, LVO, DWI, that comprehensively cover stroke imaging from CT to MR. Since JOOMED automatically classifies sequences when images are imported, AI analysis results are also generated in real time. Next, let me click the JOOMED button. JOOMED performs fusion analysis of this patient's medical images and clinical data to automatically extract key clinical results. Through this, you can see the true value of a medical imaging-based multimodal LLM. Analysis results are divided into patient level and study level. First, it tracks how the patient's condition has changed over time and provides summary analysis results. You can also confirm that the patient timeline on the left is synchronized with this. This is the guideline screen. Here, it provides prognosis overview, key prognostic factors, and follow-up management information based on global ASA/AHA guidelines. You can transparently verify which guidelines and papers serve as the basis for all information. Beyond individual experience, it provides reference-based insights grounded in global standards and in-depth knowledge. In the Study tab, when you select each study, you can see the patient timeline on the left being highlighted together. Going into a specific study, you can confirm that it provides impression overview, AI analysis results, analysis output, and key evidence along with reference sources. This is the prognosis prediction screen. It provides predictions for 3-month MRS, E&E probability, and discharge MRS for each study. What's important is explaining why these results occurred, which is supplemented through study contribution. Predicted treatment effect provides comparative analysis of predictions based on whether a specific intervention was performed. This feature was developed based on causality and statistical models built on extensive big data, and will serve as a reference tool for clinicians in stroke treatment settings where the golden time is known to be critical. Now, let me move to the JOOMED live chat screen. Here you can interact and converse in real time. Clinicians can ask questions about patients through real-time dialogue. For example, if you type, "Find me a list of patients similar to this patient," the system immediately presents a list of similar patients. Furthermore, it accurately responds to follow-up questions such as, "Among these, show me only patients whose hemorrhage volume was between 7 milliliters and 10 milliliters. Clicking View Patient Search Results allows you to view detailed information of similar patients on the main screen. While viewing these insight-based results, if you want to examine a specific medical image in more detail, you can click the Viewer tab to enter the dedicated medical imaging viewer. As you can see, it provides a medical imaging viewer with various features for professionals. You can analyze detailed medical image structure information using distance, angles, and HU values at each point. It provides functions to create training data for AI learning through various convenient annotations and labeling. In addition, it offers various features such as multiplanar reconstruction, MIP, and multi-window. In conclusion, as a medical imaging-based multimodal LLM platform, it enables in-depth examination of medical images. This time, let's try using it after changing to a preferred color theme. You can freely enter any question and get answers at any time. When you expand the screen, you can create new projects and perform various research tasks in an environment similar to general-purpose LLM platforms, including managing existing projects. You can select follow-up questions or continue entering additional questions. In settings, multi-language support including English, Korean, and Japanese is implemented, allowing immediate use in various global environments. Language-specific agents, as well as a multilingual RAG system, have been completed. Languages can be continuously added according to country-specific requirements. This concludes the demo of JOOMED, the multimodal LLM that provides insights by fusing medical imaging and clinical information. In this chapter, let me outline what's next for JOOMED. JOOMED is currently developed with a focus on stroke. Moving forward, we plan to sequentially expand into additional disease areas, including lung and breast cancer, as well as other body regions. Development to broaden this scope is already underway. Now, let me discuss our global partnership opportunities. JLK plans to deploy and localize the JOOMED platform in hospitals across various countries worldwide. We are seeking global deployment partners to build JOOMED together in each region. We are also looking for clinical infrastructure partners to ensure seamless connectivity with core hospital systems, such as EMR, PACS, and HIS. We welcome collaboration with healthcare IT companies to help JOOMED integrate naturally into hospital environments. Additionally, we welcome medical AI developers who wish to integrate their algorithms into the JOOMED ecosystem. Rather than competing, by embedding your technology into our unified global platform, you can extend your reach to a broader international network. That concludes our presentation. For more information, please feel free to reach out to JLK. Thank you for your attention.